Ciao. Okay, nice to see people here. One question I wanted to ask up front, whether we should continue doing this in person here. I heard that Pascal last time was only 4 or 5 people. I see many more people here. Do you prefer to have it in person? It's perfectly fine with me. I see people nodding. Okay, so yes, I see a lot of people nodding. So we'll continue doing this here. It's perfectly fine with me. I just, yeah, anyway. Good. So before we start, I wanted to do a little advertisement with that we're still looking for people, guinea pigs, if you want, people that would be interested in doing an experiment with us. We're looking for a total of 60 people for whom we record their behavior in a traffic scenario. I mean, essentially crossing a street. It's really interesting. So we'll have a large room. We'll do a VR setup of a street with cars coming, and you're supposed to cross the street and do similar things. And we're recording how you're moving and how you're behaving to cross the street. This is actually part of a fairly large research project that we do together with Japan. So it's a cross-cultural, so we record, so the data itself that we record here in Germany is itself very valuable, but we also will record 60 people in Japan early next year. Hopefully things will clear up so we can actually go there. And so the idea is to study, right, what are the difference for autonomous driving cars, for example, right? People behave differently in different countries. So for now, it's Germany here and Japan. And so if you're interested, where's my dark? Yes, so there's a few caveats here. So we can only accept people between 20 and 50, which I guess for all of you is okay. Normal weight. Maybe the biggest issue is you need to be a German because we want to record German and the German style of doing things. German, you're either German or spend most of your time in Germany, grew up in Germany essentially. Because we do VR, we cannot accept people who need to wear glasses, but contact lenses are fine. You cannot be pregnant, and no physical disabilities in terms of moving. So if you are interested, you'll get €22.50 plus chocolate, free chocolate. We'll take about 90 minutes to do that. It's in the DFKI here. So if you're interested, feel free to sign up. The QR code is no longer valid. So you would have to record this here, and I will ask someone to send the email around so that you have the link. So we're definitely, so we can use some more women, but not too many. We're specifically also looking for men because we're still missing more men right now. So if you are interested or you know someone who would be interested, please forward that to friends of you or whatever. Good. So that is. No, I don't want to do that. Good. So then switch over and do this. Okay, so Pascal talked about Fourier transform last time. So I was ill the last week. Sorry for that, but that happens. Things are fine again. So I'm taking back over. Pascal talked about the Fourier transform and the whole theory part, and today we'll talk about what are the consequences of all of those theory. What does that actually have to do with graphics, and how can we specifically we're talking about aliasing and specifically how we can avoid aliasing. So we'll talk about what aliasing actually is, where it comes from, and how we can avoid it. So before we do that, a little bit preliminary stuff. We looked at Fourier transforms, and we will need the Fourier transform of a delta function. So we talked about the delta function already. So that's this function which is 0 everywhere except at 0, where it has essentially an infinite value, such that if you integrate over any period, any segment that does include 0, then you get the value 1. Right, so the area of this infinitely thin pulse has area 1, but it's infinitely thin. And the Fourier transform of a delta function is the constant function, and vice versa, of course, because that is symmetric. So either it's infinitely small and infinitely high, or it is a constant and it's the same everywhere. So they're kind of complements anyway. So that's the one thing. The other thing that we will need is actually a combination of delta function, which is the so-called comb function, or sometimes also called the Shah function. So we'll have a regular spacing, infinite regular spacing of delta functions throughout the real line, with some spacing delta x here. And then if you take the Fourier transform of this comb function, you also get a comb function in the Fourier space, but with the inverse spacing, right? So if you make things spacing smaller on in the spatial domain, you get a wider spacing in the Fourier domain, and vice versa, right? So that's as much as we need to know. I mean, of course, you can do a lot of math proofs there, but we're not so interested in that. We can deal with things at that level. So yeah, so that's essentially just what I said, or what I already said. So if you have a constant function f of x with value k, then the Fourier transform of that is capital F of omega, which is then k times the delta function, and the other way around. And for the comb function, as I said, inverse wavelength, and the amplitude scales with the inverse wavelength. So the amplitude, it's infinitely high, but integrating over is not 1, but the inverse of the spacing of the wavelength. So, and why is that comb function so interesting? Well, it describes how to sample a signal with how to regularly sample a signal. So if we assume here at the top, and I hope now this works. Does that work? No, it does not. It worked in the previous. I'm not sure what this thing is doing. Okay. I tried it with the other presentation. If anyone has a good idea of what I do wrong, then let me know afterwards. Anyway, we'll deal with. I'll use the pointer here. So let's assume we have a continuous function f of x here, and we have its Fourier transform. And these are symbolic representations, right? So this is not, the function don't have to look like that. Just say we have a regular function, and we have its Fourier transform, and we'll represent the Fourier transform simply as this pyramid function here. And what we want to do now is the continuous function. We want to sample it, regularly sample it. So what do we do? Well, in the spatial domain, we simply take a product of the function f of x with that comb function, which means the result of that is 0 everywhere, except at the positions where the delta functions are, where we now get f of x times the delta function, right? Because it's a product, right? So essentially the function breaks down, it's 0 everywhere, except at those positions where we sampled it, where we then have a value that is in some sense proportional to the function f of x at that sample point, which is exactly what we want to do if we want to sample a function. However, now we know, right, what happens in the Fourier domain. Right? If we multiply in the spatial domain, that means we do a convolution in the Fourier space. Now, what does the convolution do in the Fourier domain? Well, first of all, there's this relationship of the sampling pattern. So the spacing is inverse. So if you have a fairly dense spacing in the spatial domain, this means we have a wider spacing in the Fourier domain of the comb function, right? So what does what does convolution now means? Well, you shift this pyramid function over the comb function, right? And you and what that does, it projects out wherever there is a peak. You get a copy of the Fourier spectrum of that pyramid function, of that spectrum of the function f, right? That is what convolution does, right? If you think about this, you shift, you integrate over that, you get an exact copy centered at each of the combs. So get an infinite copy of the spectrum of your function f. That's strange, right? But obviously that's not what we want, right? We want something that we want a sampling where we can transform back and get the original signal, right? We want to be able to do that. We want to take a function, want to sample it, have a discrete representation of our function, and then we want to go back and have the original function. So essentially interpolate those sample points and ideally get the original function back, right? But what we get is obviously not the original function, because that would be that single peak here. And instead of the single, where's my pointer? Instead of the single peak, we get an infinite number of those peaks, okay? So what do we need to do to get back our original function? Or actually, I'm getting ahead of myself here. So now here we're only talking about sampling. Okay, so now let's think about what happens if we change the sampling frequency. So we take more samples, right? If we take more samples in the spatial domain, right, then those copies are spaced further apart, right? Because the spacing is inversely related to the density of these delta functions, right? Or vice versa, right? If we in the spatial domain sample more seldomly, those samples, those copies are getting closer together. Okay, let's assume that we have a band limited, frequency limited function. All right, so something that really has zero frequency beyond some highest frequency. So right, our frequency spectrum stops somewhere. It's zero outside of that. Okay, if we do that, right, and we make sure that these copies don't overlap, that will be good, right? Because then we can maybe we get rid of all the copies, we just keep the center one. And if we only keep the center one, we can go back, right? However, if we have a signal that has infinite frequencies, right, we won't be able to do that, right? We can't just put them far enough apart, right? Or if the support is fairly large, right, we might not be able to sample densely enough in order to move them as far away that they don't overlap, right? If they do overlap, right, we now have a problem. That is called aliasing, right? Why? Well, you think about what we want is this single copy here, right? But if you have overlaps, right, you cannot keep them apart anymore. There's nothing you can do, right? If you add up parts of the copy, or one or more copies, there's no way you can differentiate between what is coming from a copy and what is not coming from a copy, right? So the simple process of sampling a function, right, and not making sure that the frequency spectra don't overlap in the Fourier space, creates an artifact, and that is what we call aliasing. This is marked in red here, right? Because we can never, whatever we do, we cannot get rid of that red part, okay? And so if we want to reconstruct the original function, it's impossible, right? The mere fact of sampling and mixing in the frequency spectrum destroys everything. There's nothing you can do afterwards. Just sampling in the wrong way screws everything up. And we'll see how these artifacts actually happen. You can kind of guess this already, right? So what happens is that the high frequency spectrum of the copy, let's say to one side, right, that overlaps into the original copy at zero, centered at zero, right? So high frequencies of that copy show up as low, right? If you shift them, it shows up at low frequency in the original signal. So you get artificially low frequency signals into your original, and that's what we will see, right? That's how it visually appear, aliasing artifacts appear, right? So in order to avoid that overlap, there's two conditions we need to meet. The one is we need a band limited signal, so the frequency must stop somewhere, right? If they continue to infinity, we cannot move them far apart, right? And if it is band limited, we have to sample with high enough frequency that the copies are far enough apart. And this is exactly where the Nyquist limit comes from that Pascal talked about last time, right? Because the frequency goes to both sides, right? So if we want to space them far apart, we need 2 times the highest frequency, because the extent of this triangle, what's here symbolically represented as this pyramid function, the width of that is of course twice the highest frequency. So we need to make sure we sample densely enough that those copies are twice the highest frequency apart from each other. Otherwise, they start overlapping. Okay. So that was the sampling process, and really, it's important to remember that the damage is done as soon as you sample. Okay, not somewhere later. And so what we would like to do, obviously, and this is nicely shown in this graph here again, so we have this original function. We have, again, symbolically, its frequency spectrum. We assume it is band limited, so it stops somewhere. There's no content beyond some highest frequency. We're sampling this, so this is our sampling function, the comb function. The Fourier transform, again, is a comb function with maybe a wider spacing in this case. Then if we multiply the two, we get the multiplied, right? In some sense, the delta function scaled with the function of the function value at the sample location. We get those replicas, right? And now if we want to reconstruct the original function, if they don't overlap, right? We can now do a box filter, for example, cut off everything that is all the copies. We just such that we retain just the center copy, which is the Fourier spectrum of the original function, right? Everything else is gone now. And then we can do an inverse Fourier transform, and we end up with the original function, right? Even though we have this original smooth continuous function, we represent it as a finite set, possibly infinite set of samples, but discrete number of samples. Okay, it's no longer a continuous function. It's just a set of sample values, right? And then we can go from the set of samples, we can go back by the reconstruction, by cutting off the copies, we can go back. And we get, ideally, if there's no numerical and other mathematical issues, we get back the original function, which is quite impressive, actually, right? You have a continuous function, which cannot have too high frequencies, and then just sampling it high enough, we can reconstruct the original function exactly, mathematically at least. Good. Yeah, I forgot to say something. So a box function, so we want to cut off everything outside of the center copy. Ideally, we use a box function for that. Now, box function, if you actually, right, we might not do the reconstruction actually in the Fourier space, then a box function is simple, but we typically do the reconstruction on the spatial side. But of course, the Fourier transform of that box function is a sinc function, which has infinite support and has negative slope, has negative components to it. So the reconstruction with the sync function is not always unproblematic. We need to be a little careful here. And so what people come up with say, okay, well, maybe we don't take the sync function. Maybe we cut off the sync function, right? Because we want a finite support. It's easy to do computations that way, much faster, infinitely faster, actually. But however, if you do that, right, you're not getting the box function, right? We remember that we got the box function by adding an infinite number of frequencies, right? If we take some of the high frequencies away, we get these ringing artifacts of the box function. And of course, that has consequences for the original signal, because we don't just get 1 times the original signal, but that's, right, maybe it wiggles between 95% and 105%. And that will, of course, not reconstruct the original function, but some variant of that. So we need to be very careful to use a reconstruction filter that is as close as possible and doesn't modify the Fourier spectrum. So if we put this all together, so this was more symbolic on the previous slide, so let's look at a real signal. So this is actually a scan line of an image here on the left, this f of x. In this case, it's a band limited signal, so we made sure we don't have any high frequencies in there. You see this, that the Fourier spectrum is 0 out a little bit further out here. So we only have frequencies until about 1/2, okay? Or actually exactly 1/2. Then we sample that. So we have a discrete number of samples, and we just set this up with just a high enough frequency that we can, that these copies do not overlap. And then ideally we use a perfect box filter for reconstruction. And now if you look at what that sync function actually does, and I hope this is somewhat visible here on the slide, what the sync function does is the sync function is 1 at the center, right? So it projects out this 1 sample, and it just goes through 0 where all the other samples are, if you have just the right sync function, the perfect box filter here. And so essentially you just project out this 1 sample, and then if you do this for every sample, this reconstructs the original continuous smooth function. That's just applying what we learned in the last lecture. So yeah, so if we now, however, let's assume we have the same input here, and we're instead of the sync function, right? Where maybe we don't like the negative parts of that. Let's assume we'd use a sync squared function instead. So that would, instead of the sync function for reconstruction, sorry, so instead of using the box function in the Fourier space and the sync function in the spatial space, let's assume we use the sync squared, which is the tent function. If we use that for the reconstruction, then yeah, you kind of see that again we get aliasing artifacts, because we're now including components of the copies in the reconstruction process, and of course that will not yield the same function. So we again get aliasing artifacts. They're now due to the reconstruction, not due to the sampling process, right? The sampling process was fine. The copies were, right, did not overlap, but we did not use the perfect reconstruction filter, right, which still mixes in parts of the copies, and that results in reconstructing, obviously not of the original function, but some variant. And you see this here in the image. Yes, and if we sample at too low frequency, so the spacing is too wide in the spatial domain, right? Which means that the samples get too close in the Fourier domain, even though we have a band limited signal, they start to overlap, right? And now the error already happens in the sampling process. They overlap, and there's no way, right? No reconstruction filter can tell them apart anymore, right? So it's too late, And if we now do reconstruction, or even if we have a perfect reconstruction filter, like a perfect box filter, right? You've already mixed the two signals with a copy, the one signal with a copy. There's nothing we can do, right? No way we can deal with that. And so we get aliasing. In this case, the aliasing comes from the sampling process itself. And again, if then you don't use a perfect reconstruction filter, I mean, it's too late anyway, but if you use a bad reconstruction filter, it just gets worse, right? I mean, it's kind of clear, which is all of what that slide here says. So just to drive this home, here's a different representation of what I just tried to tell you, because it is so central in graphics, okay? So let's assume we have that original, and again, this is a symbolic representation here, right? So we have, let's assume, so there's two cases here, and we're only looking at the Fourier space in this case. The one case where we sample with a high enough frequency, right? So we have the original spectrum, and again, they're band, so these half circles or whatever that is, they end somewhere. So there's no high frequencies, or there is a finite highest frequency. If we sample with a comb function, again, we get these copies, and where the Nyquist limit is satisfied, so we're sampling with at least twice the highest frequency. That ensures that the copies are separate, they don't overlap, right? And then with a good reconstruction filter, we can eliminate all the copies. We have the one frequency spectrum left, and we can transform that back and we get the original function. Everything's fine, right? If you look on the right-hand side of, in this case here, again, the signals overlap, the spectrums overlap because we didn't sample high enough, and there's nothing we can do. And here's on a 1D signal, essentially demonstrating what I just talked about. Okay, so here we have a sine function, right? And we're sampling that sine function. So the highest frequency is clear, is two samples per wavelength. And so here we obviously have many more samples per one cycle of the wave, right? So perfectly, and we can, from those samples, we can certainly reconstruct the sine wave. Okay, no problem here. If we are exactly at the Nyquist limit, right, which means we have exactly two samples per wavelength, this is already not good enough. You need to sample with, right, at least an epsilon better than that, right? Why? Well, if you're, so this kind of the worst case here is that you sample, just happen to sample whenever that sine wave is 0, okay? And then it seems like you're measuring the 0 function. There's no signal. It seems that there is no signal, but you just happen to have bad luck here. If you shift that by any amount, you can get whatever value, constant value that is between -1 and 1, right? It's always constant offset. It's it's not a constant function, but it will be a sine wave, but it will not be the sine wave that you're getting, because it seems like so you get a positive value and negative value, but not the full amplitude in this case, right? Just think about shifting those samples here by, I don't know, a little bit to the right. You get a signal, and you get a negative signal for the next sample, and again. So, but if you want to interpolate this with the sine wave, right, you get a sine wave with smaller amplitude. This is essentially demonstrated here in the lower left, where we are sampling with slightly above the Nyquist limit. This is obviously complete bullshit. What's on this slide? Oh, no, sorry. I was reading this the wrong way. So here, the spatial frequency of the in the top left, the spatial frequency of the signal is smaller than the sampling limit. All right, that we have given the sampling pattern. Right, and here in the lower, that was the top left. In the lower left, we have the spatial frequency of the signal is higher than our sampling, than the Nyquist limit. And so in this case, we're reconstructing a sine wave with a different, an alias signal, right? And this can get really bad here. So if it's much larger, it seems like you're actually reconstructing a completely wrong sine wave that's not there, but it seems to be there. And actually, you probably know that effect in acoustics. You might have seen this, that did the experiments in school, right? If you have two Stimmgabel, what's that in English? So two tones, two sine tones that are almost the same frequency. What you hear is actually, it's called Schwebung in German, and I should have prepared better. I don't know what the word is. Maybe someone can help me online. Anyway, yeah, it's not that important. So here's the same thing in 2D. So essentially here we have an image of a signal that gets higher and higher frequency the further apart, the further away you are from the center here. So it's a low frequency in the center, and that gets higher and higher frequency to the outside. And we're sampling that with the sampling pattern that you see here in the middle, right? And if you then reconstruct a function out of that, you see that in the middle it's fine, right? In the middle you get the original function because the sampling pattern is higher than the frequency and the spatial frequency of our function. And the further you go outside, you currently see low frequency patterns that are not in the original signal, right? That's exactly right. The high frequency of the copy shows up as low frequency, right? We do a reconstruction, but we've added a low frequency to that center component, and we cannot get rid of that, right? So we just happen to see these low frequency effects here, and that is aliasing in 2D. Here's other artifacts. So these steps, right? If you sample this rectangle here on the left, right, with finite number of pixels, you get this step pattern on the edge, right? Again, we know edges have increment, right? That's similar to a box function, right? There's one, and then suddenly you're at 0. In order to represent such a sharp edge, we have infinite frequencies. So if we cut them off or get some, right? Obviously, we cannot, with any finite number of samples, can we represent such a sharp edge. And one of the effects we get out of that are these edge artifacts. So that's also an aliasing artifact. And just to visualize this a little bit, here in the middle, you see the Fourier transform of these signals. Don't want to go into too much detail here. Here on the right, this is much more important, or much more interesting. So this is a checkerboard pattern, the perspective visualization of a checkerboard pattern. I mean, the checkerboard pattern itself obviously has a constant frequency in terms of the checkerboard cells. Obviously, it has infinite frequencies at the border between the black and white tiles. And in the front, everything is fine. I mean, obviously we cannot perfectly represent those edges, but the frequency is high enough that at least we don't see any aliasing that comes from that. But if we look in the back of the image, right, where through the perspective projection, there's more and more tiles that project onto a single pixel. And what happens is that you see low frequency artifacts appear where there should be high frequencies, okay? And so, right, for instance, there's these patterns here, right? You see this very clearly where a whole number of pixels are all black, right? Where it should be high frequency changes between black and white. right? Why is that? Well, we just happen, there's high frequencies in the signal, and whenever we sample, we just happen to hit always a black tile. Okay, and that's why we get a low frequency black pattern here where there should be high frequencies. Again, right, there's a high frequency component from one of the copies showing up as a low frequency element on the original, in the original spectrum that we then reconstruct this image from. I mean, conceptually what's happening there. Yes. So the cause for aliasing, it all comes from the most important source in graphics is the sampling process itself, right? Again, I showed it can also come from bad reconstruction, but usually we can do something about that. There's nothing we can do about the sampling process itself, right? We multiply with that comb function. The comb function causes that replication in the Fourier spectrum, and there already we mix up stuff if it's not band limited and if the sampling frequency is not high enough, and after that there's nothing we can do. The issue always comes up if we have a non-band limited signal, right? If we have band limited signal, at least we could theoretically deal with it, but in graphics we just have edges, right? If we render an image, right, there's the chair or there's the background, right? There's an infinitely sharp edge in the projection here. There's shadow, we'll come back to that. There's shadow boundaries. There's I mean, we cannot avoid sharp edges in graphics. Right? Simply no way. They are in the 3D, in this 3D scene, there are sharp edges. There's nothing we can do about this. So it's impossible to generate a image without any aliasing artifacts, right? Because we have infinite frequencies, we cannot represent it. The best we can hope for is that the aliasing artifacts are small enough that we don't see them. If we do graphics, we'll come back to that. In reality, if you use so one question is, if we have a camera, why don't we see that? I mean, yes, you can see this in cameras, but there is a difference in a camera, right? Because a camera has a finite size pixel and it integrates over that pixel. So it's not, the camera does not perform a perfectly point-wise sampling process, right? It actually integrates over a finite area. It's not what we covered here. Here we assume we do infinitely thin samples with the delta function, right? So we're talking about something that is different. As we'll see in a second, that is very, very hard to do in graphics. Okay, the point here is that the projection of the light function onto a film with finite size pixel, essentially you're performing a filtering process in the analog domain, right? That's the integration of whatever light arrives at this finite size of pixel. You integrate over all the photons in the pixel. That is an analog integration process. We're not, right? We're then sampling the result of that integration process, right? But we have done a filtering process before that in the analog domain, right? Before we then discretize the signal. Right? That's why we have less of a problem. So essentially, this filtering with the individual pixel, that removes high frequencies already. However, in a computer, right, if you think about ray tracing, we cannot perform this analog integration. We only have a single ray, right? We'll talk about this a little bit more in a second. So we have to do point-wise samples in many cases, and we're doing the damage by using that infinitely thin sample already. So the only way is really to do numerical integration by doing many point samples and maybe averaging over that. But again, the point sample already does some of the damage. And it's computationally expensive. We'll talk about supersampling in a second. Yes, and it's important to keep in mind, right? There's errors that happen in the sampling process, right? Because of, as you sample, we get the overlap, nothing we can do about this, but we can also generate artifacts in the reconstruction process by not using the proper or the right reconstruction function. So sampling artifacts, essentially you saw some of them already. We have these SAR cases. The more, I forgot to mention, maybe I should go back here. So this is typically called Moret pattern. So this is what I just talked about. This is essentially interference patterns. You also see this if you have any more or less regular pattern on a transparency, on two transparency, you kind of overlap them. You see, again, you see frequencies appearing that shouldn't be there.
Philip,
so what
Philip, there is a question.
Yes, there is a question. Thank you. I didn't fully understand why the high frequency components get mixed up with the low frequency components. Since Fourier transform of a function is symmetric, should we have high frequency getting mixed up with high frequencies again, because the end of one replica and the beginning of the next are both high frequencies that get mixed up? Yes, that's actually correct. If you only, right, if they only overlap a little bit, right, then you get high frequencies showing up at the other high frequencies. But if they start overlapping a lot, right, then the high frequencies of the copy can actually show up as a low frequency, and that's what's happening, right? So the overlap is actually much stronger in those cases. And you can see this. Let me go back to this checkerboard pattern here. Right, the frequency is much higher of the signal is much higher than the sampling pattern of the pixels here, and so the copies are very close to each other and they overlap a lot, and so that's where the high frequency of the first copy for example, show up as a low frequency in the original copy, in the center copy. Does that answer your question? I think it does. Okay, so next question. Yep. So yeah, what is the solution? Okay, well, we can increase the sampling rate, right? That helps, but not in graphics where we have lots of infinite frequencies, right? Because we cannot obviously increase the sampling frequency to infinity. So people have suggested post-filtering, and we'll talk we'll have some example of that in a second. So essentially after or during the reconstruction, right? And as we just discussed, it's impossible. You already mixed up the two signals and there's nothing we can do, right? So doing any filtering after the sampling process doesn't help. We could do pre-filtering. I talked about this, that the finite pixel size does some of that. Yes, that is possible, right? As long as you stay in the analog, or you do any sort of filtering in the analog domain, everything is fine, right? If you use filtering in the analog domain to remove some of the high frequencies before you then sample, then things might be fine, right? If you remove the frequencies that would cause aliasing, right? But that's very, very hard to do, right? If you generate an image, right, there are edges, and how do you filter the geometry that it has a smooth edge, right? It needs to be transparent. That doesn't really work. So pre-filtering in theory is a solution, but not for us in graphics, really. So there is one solution, and we'll talk about this in a minute, that is super sampling, right? It's kind of contradicting what I said, increasing the sampling rate doesn't help. It doesn't eliminate aliasing, but by increasing the sampling rate, we can reduce aliasing, right? So we'll talk about this in a second. So, but before we get there, let's look at other sorts of aliasing, and you all know them from TV and the movies, right? You've all seen cars or cartwheels turning in some old Western film or whatever, and at a certain frequency they seem to turn backwards, right? And the result of that is, and this is kind of what I try to demonstrate here poorly, right? You have a cartwheel that turns a quarter of a degree between the, so these are individual frames of the same cartwheel next to each other, right? So, right, they turn by quarter circle between each sample, okay? However, so then things are kind of okay, right? However, if we only sample every third frame, right, they seem to turn a quarter of a circle 90 degrees in the opposite direction now. That's exactly what you're getting. Okay, post-filtering again doesn't help. Right? Just filtering these 3 red copies, what do you get? Well, you get a smeared out or blurred version of those, but it doesn't help you generate the right motion in the forward direction. So, and pre-filtering doesn't work either, right? Because we would have to do this in the analog domain, and no one knows how to really do this. Yeah, so sometimes you can do that filtering before, right? By if you do it in the analog domain, essentially, right? If you smear something on your lens, right, that will blur the image, which essentially what we talked about filtering, band limiting signals, or eliminating high frequency. That's a blur operator, so you can put some smear something on your lens that blurs the image, which means you're removing the high frequencies, which means now you should be fine to sample your signal. But of course, you're not getting the original function that you're interested in, right? So yes, it might be right, and you need exactly the right blurring there. So in many cases, that doesn't really work either. Yeah, essentially, I already talked about this. So edges are a key element of where high frequencies come from, sharp boundaries, silhouettes, right? The silhouettes means that it's not just the edge of a geometry, let's say the edge of a triangle, right? If you have a perfectly smooth sphere represented analytically as a sphere, right? You still get an edge, even though there is no triangle edge at the silhouette, right? But by doing the projection, you obviously get a perfect edge in the projection. The high frequencies can come from geometry. They can obviously, as we saw, come from textures, right? Your geometry might be perfectly smooth and no problem. Right, but if you have a checkerboard pattern on top of that, well, it has exactly the same problems. It can come from illumination, so a sharp shadow edge, some projective texture mapping, things like that can obviously cause the same problems. And any analytic filtering that's the other thing is essentially impossible. So what people actually have tried to implement is they've tried to do what cameras are doing, right? So instead of representing a pixel with a single sample, let's say in the center, which we do in ray tracing, right? They have tried to do that pre-filtering step. So they've represented the pixel as a rectangle or as a circle. And if you then render a triangle, right, you're looking for the overlap of that sphere or of that circle with a triangle, right? And if you only look at an edge, then actually computing how much of a single edge, how much it overlaps with the circles, that's actually not too complex. So you can actually analytically integrate how much of that triangle color bleeds into or contributes to this pixel, and that would be that analog filtering step, right? However, there is a problem with that because yes, we can do this for an infinite edge, right? But we can't do it at the vertices, right? Because then they overlap, and it's much harder to determine how much at the edge of a triangle, at the vertex of a triangle, how much of that triangle actually overlaps with a pixel. So things get so complicated that it just doesn't pay off to do that. And adding to that, the triangle gets smaller and smaller. So because we have more complex geometry in our scenes today than back in the time when they tried that, they had few large triangles. Now we have very tiny, very tiny triangles if we render stuff. So you never have the case where there's one long edge overlapping a pixel, but essentially you only have vertices and or at least lots of these vertex in pixel case, and that becomes essentially unmanageable. So here is, however, how we are able to reduce aliasing, right? We cannot eliminate it. Again, we have infinitely high frequencies because of sharp edges, but here's how we can deal with this. Remember, and that's really the key part. When you looked at typical signals, and we did this in the last lecture, the typical frequency spectrum had a peak at low frequencies and falled off, the amplitude falled off towards higher frequencies fairly rapidly. Okay? So remember, aliasing happens when things start to overlap. Okay? However, the signal gets lower and lower the further out you're going. Right? So if the overlap is only out there somewhere, then it's very small. Right? The overlap only contributes very little to the original function, so the aliasing is small. Okay? So here's how we can do things. And actually, this is being used in many kinds of audio processing. You certainly heard about oversample, and if you look at the spec sheets of some audio processor, right, they talk about so many times oversampling. That's exactly what they're doing. So they are, when they sample the original signal, right, they use a much higher frequency than what they finally can store on the CD or whatever, right? Whatever your sampling rate is with which you store your music signal. You sample the continuous audio signal at a much higher frequency, okay? And we call that high frequency F1. Because we sample with a high frequency, right, we're shifting those copies far apart, and the overlap is small, or the overlap where there is overlap, because they fall off quickly, right? Where there is overlap, it's now smaller than if the copies were closer together. Okay, so we've reduced aliasing here. We haven't eliminated it because we have infinitely high frequencies, so we cannot eliminate it. But we've reduced it, okay? However, now we have too many samples, right? Because I don't know, we did 8 times oversampling or 16 times oversampling. So we have 16 times too many samples than what our target rate is that we can store things at, let's say. So we want to go down to, let's say, only an eighth of the samples, okay? And that is maybe our frequency that we actually want to store things at, and we call that F2, right? And the interesting thing is we've done damage when we sampled with F1, right? But that damage was small. So what we can do now is we reconstruct as good as we can. There will be some aliasing in the reconstruct, but we reconstruct a continuous signal as good as we can, given the high frequency samples we've taken. Right? And again, there will be small aliasing in there. Now we have a continuous function again, and now we can sample that continuous function. So we can reconstruct the continuous function, and now we can perform filtering on that function, right? We can filter away the high frequencies. We're not doing a sampling step, right? Filtering is fine. We can just, right? We have a finite discrete number of samples, and we can perform a filtering operation on these number of samples. Okay, right? We can go into the Fourier domain, cut off all the high frequencies, transform back, or however you want to do the filtering step. We have a discrete number of samples, and we can perform filtering. We can remove the high frequencies. right? And now we can sample that, right? We've removed all the high frequencies that are, let's say, higher than f2, and now we can sample with f2. So we sample with a high frequency, we reconstruct the continuous function, small in the discrete domain, remove the high frequency, and resample that function, where the high frequencies are no longer there. And now we're not introducing new aliasing, because we've made sure there are no high frequency, so there's no overlap at that sampling, at that second sampling process, right? And the nice thing is that you can do all of that in the digital domain, right? The problem happens at that first sampling. That's where you introduce aliasing, but we just make sure with the high frequency, the aliasing is small. All the rest is just digital processing. And we're not adding any aliasing in that process. If we do things correctly, right? I mean, as we talked about, if you use the wrong reconstruction filter, yes, of course, you're adding more artifacts, but if you do this in a good way, you at least have the chance not to introduce new aliasing in that process. So again, sampling with a high frequency F1, there will be some aliasing. So that's essentially this, right? Where there's aliasing because of this blue part here out there, right? Only that will cause aliasing. The inside is fine because we sampled with high enough frequency, but right, the function is almost 0 out there. So the aliasing will be small. Then we using some filter G1, for instance, a sync filter with respect to the function F1, the frequency F1, right? We can filter, and we now have a reconstruction, and then we can essentially low pass filter that signal with some filter G2, and then we can resample that. We can sample that. And the nice thing is that these function G1, these two filters G1 and G2, which reconstruct the function and then low pass filter, then you can actually just essentially multiply those two filters into one filter. So essentially you sample with a high frequency, you do a filter operation with this combined G1, G2 thing. The result, since you're in the digital domain, is essentially just the samples that you want with respect to F2, which is your target frequency, which is much lower than F1. So how does that look like in graphics? Well, we call that super sampling, right? Instead of taking a single sample, right? So far, we always said we trace a single ray through the center of the pixel, right? Why not trace more samples, right? For example, let's take 2 by 2 samples in each pixel, and we distribute them evenly across the pixel, right? Actually, 4 samples gives you, for typical scenes, give you fairly good results already. You could go up to maybe 4 by 4 samples, so 16 samples. That typically for a lot of scenes that actually gives you pretty good results already. On graphics side, we usually, right? Ideally, we use a box filter in the Fourier domain. There would be a sync filter. That's really unwieldy. So we typically use simpler filters. Yes, that includes aliasing, but we've hand sampled high enough, so hopefully there won't be too much. So yes, you have to optimize these filters, but in many cases, actually a box filter is not too bad. Box filter in the spatial domain. So what other sampling patterns? So there could be the regular sampling, right, that I just showed you. So there's other sampling patterns. So we could randomly sample in a pixel, right? Just choose a random uniform number for X and Y and sample at that location, do that 4 times or whatever n is, and you sample n times within a pixel, right? That actually is not too bad, but it's actually not good. Why? And we'll talk much more about this in the realistic image synthesis course. Well, it's not good because you're doing it random, right? Random means it could happen that all the samples are in the lower left-hand corners, right? They could all clump up in one corner, and you don't get any effect of that, right? They essentially all get the same. It's as if you take just one sample. Right? There could be large parts, there could be gaps in the pixel that are not sampled at all. Yeah, so actually random sampling is not a very good idea. It's not bad, but it's not a very good idea. We'll see we'll talk about why random sampling actually has another effect that is nice. but it can create clumps and incomplete coverage. Poisson disk sampling is something that is much better. Poisson disk is you assume a certain radius around each sample point, and you just make sure that within this radius no other sample point is. So there, essentially you introduce a minimum distance between the sample points. Right? Of course, that radius has to correlate with the number of samples you want to generate. Right? If you make the radius too big, you can't add more samples to it. So that's a little bit tricky, can be tricky, so you have to adapt this. Also, sampling enough pixels, enough samples in a pixel can be also quite expensive to find good samples if you do this on the fly. So most of the time you're using Poisson disk sampling is you pre-compute some good sample patterns and then just use those. There is a different form. So one way to get rid of the problems of random sampling is you don't make it perfectly random, right? So for example, you subdivide your pixel into 4 subpixel, 2 by 2 subpixel, and then you randomly sample each one of the subpixels. So one sample in each of the subpixels. So that kind of makes sure that the samples are more evenly distributed, right? Of course, it could happen that they all clump now in the center where the 4 subpixels meet each other, right? Okay, if you use 3 by 3, then at least that cannot happen anymore. The other thing is you focus them on the center of the subpixel, and you only allow a certain deviation from that center, so they cannot clump in the center. Actually, what hardware does is something that we call a rotated grid pattern. So essentially, it is a regular sampling, but essentially the pattern is rotated against the grid of the pixels, and that has a number of advantages. It's because right, straight edges align neither with the even if they align with the pixels grid, they would not align with the rotated sample grid, and vice versa. So you do get some benefit from that, and it's simply enough that it's very efficiently can be done very efficiently in hardware. But with newer hardware, you can actually load the sampling patterns and where those samples are being taken per pixel. Yes, so let's talk about some caveats. So one thing that a lot of people think about is, oh, super sampling is expensive. Can't I get away with this, right? If you do 4 samples, that's 4 times the number of rays. So you spend 4 times as much work. Can't I do something about that, right? So the common idea that people do is, well, let's not filter in the center of a pixel, but let's sample not in the center of a pixel, but sample at the edges of a pixel, right? And then I simply average those results or do some linear interpolation or whatever. Can someone see what the problem with that approach is? What's the frequency of the sample pattern compared to the frequency of the sampling in the center of a pixel?
Is there a problem that we are sampling at the same frequency?
Yes, exactly. Thank you. Yes, it's exactly the same frequency. Right? We just shifted the pattern to half a pixel to a side, but the frequency, which is all we talked about, is exactly the same, right? Which means you're getting exactly the same aliasing artifact. Okay? So what are you doing? Well, you're doing a post-sampling interpolation, a blurring operation, right? So you're blurring, so you've done the error, and yet now you're blurring your error, but the error is still there. You just blurred the error, right? There's no advantage in doing it. Well, there's a little, because you add one more sampling at the edge of a pixel, right? You shift it to the top or left, so we add one more line. So yes, you could say there's a little bit, but essentially the frequency is the same, right? So we're not gaining anything really. Yeah, so doing the blurring operation, right, is exactly right. We get a blurred version You see the step pattern, right? We get blurred steps, but the steps are still there. So no, it doesn't help. It's not a solution. So the thing to remember is, right, there's no free lunch and there's no free super sampling. Right? Either you take the samples, that is when you, more samples, then you're getting the benefits of that. But not taking more samples or sampling at a higher frequency, which is the same thing, then you're not getting anything out of that. However, there is one thing where you can play around with the sampling pattern, and that is adaptive supersampling, right? If I want to render this white wall here, right? Why on earth do I have to take 4 samples per pixel when the function is essentially constant, right? There's no point there, right? So if I knew that the signal is essentially constant or linear or smooth, let's say, in general, then there's no point in taking more samples, right? I know my function has low frequency and I can get away with few samples, right? Because Nyquist limit is nicely enforced. So I would have to locally decide what the frequency should be, right? And so what do I use, for instance, to decide whether I need more samples? Well, you could simply look at the difference of pixel values to neighboring sample values, right? If the sample differs too much, you say, well, there's something going on here. Maybe I should take more samples, right? Often we don't look at the difference, but we look at the contrast. We'll talk about the human visual system, and we'll see that contrast is actually more important than the absolute value. And so actually contrast turns out to be a better measure for difference, and we typically don't do this in the RGB domain, but in some better domain that better measures color differences, right? Because we care about color differences. And turns out that, right, even the same difference in absolute RGB values in the green domain is perceived very different than the same error or the same difference in other parts of the color spectrum. But we'll get there later. So here's one. There's actually many techniques of how to do adaptive supersampling. This is one. Here you actually do start sample at the corners, and you do one sample in the center of a pixel, okay? And so what you now do is you recursively look at the quadrants of this pixel, right? And if let's look at, so essentially we reconstruct the pixel here as 1/4 times what the quadrants, the value of the quadrants. So we essentially do an averaging of the quadrants, of the 4 quadrants of this pixel. What do we do per quadrant? Well, we average the center value. So in this case, E here with, let's say, A for the top left quadrant of this area here, right? So essentially for this quadrant, we use the center value to represent this triangle here, and the edge value here to use the other triangle, subdividing this subpixel here into 2 triangles, right? We do the same thing for this subquadrant here, because let's say the center value and the edge value are more or less the same, right? You decide not to, that you don't have to subdivide, right? So you just use those 2 values. However, in the top right, we see that the difference between, in this case, B and E is too big. The difference or the contrast between those samples is too big. And we say, oh, here's something going on, right? I should take more samples. And then you just recursively do the same thing, right? So now you take this subpixel, you subdivide it into 4 subpixels in some sense, and you do exactly the same process recursively. And then you continue, right? In this case, right, for these 3 quadrants, we're okay. And then for this one here, again, we take some more samples. And so on. And at the end, you see this recursive formula here, right? So A and E 1/2, D and E 1/2, because we didn't subdivide. And in the other case here, we take 1/4 So again, we have 3 quadrants where we don't have to subdivide. And for the 4th one, again, we take 1/4 of the 4 quadrants of this sub pixel in this case, and so on. So it's a very easy scheme. You have to determine when do you subdivide and when you don't. And if you want to do an extension, instead of using the exact pixel point, we might jitter them a little bit. We'll talk about why jittering can actually be a good thing in a second. Yes. So what's the drawback of this method? Any ideas? Online? Any ideas online? What's the drawback of this method? What can you miss? I give you a hint. Come on. Well, first of all, we don't have to start with entire pixels. You can also start with, let's say, areas of 4 by 4 pixel, and you keep subdividing into 2 by 2 pixel, into 1 by 1 pixel, and then you can go to subpixel, right? But of course, what can happen, you can miss small features with the original sampling, right? There might be a very thin triangle going through that pixel, which you never see, right? And so you will not reconstruct that part of the triangle. Right, so these kinds of things actually can happen. You can kind of deal with this if you see that there's something going on in the neighboring pixel or neighboring region. Then you right, if you start subdividing there, then maybe I should also subdivide the neighboring pixel along the same edge. But then the whole algorithm gets more complicated, and then you have to kind of backtrack and maybe subdivide something that later you see there's something happening here, and then you need to backtrack and maybe follow the triangle that you've missed before into a number of pixels. So it's a very nice approach. It's being used in some cases, but if you want to be fast, this is maybe not the best method. I kind of hinted that regular sampling is maybe not the best approach, right? However, it's the only approach that Fourier transforms or the Fourier theory can tell us anything about, right? The Fourier analysis assumes we're doing regular stuff, okay? So the theory of Fourier transforms doesn't really apply if we're not doing this regular sampling, right? In particular, what I talked about, the comb function, right, doesn't apply if my samples are somewhat random, or at least not regular. What we can do instead, or let's point out the problem first, right? If we have a regular, let's assume we have this really high quality 4 by 4, so we take 16 samples per pixel, right? That's a lot, right? It's more than an order of magnitude more work that I'm doing. And if I'm unlucky, I'm not getting a lot of benefit, right? If I happen, for example, to have a horizontal edge that, let's say, moves slowly up, let's say I do an animation, right? And I'm moving this horizontal edge slowly up. Let's say it's white above and the edge and black below the edge, right? And I'm slowly moving that edge forward, right? What I can do, I can actually represent 60, let's assume we do this in black and white. So a sample is either there or it's not, right? So what I can get is actually 17 levels of gray, right? It could either be all off or they could be all on. However, if I now shift this edge, horizontal edge, across this pattern, right? I'm not getting any well, I'm getting a benefit, but it's only 4 events. I only get 4 levels of gray, right? Because it just switches on an entire line of those samples, right? And actually that happens quite often. If we have man-made scenes, there's a lot of vertical and horizontal edges because that just happens to be how we construct a lot of man-made geometry. If, however, we randomize our samples in some way, so they're not regularly organized, right? whatever I do, I will never essentially, or it will be very low probability that I actually switch on more than one pixel at a time as I shift something through it. So here is very clearly to see that randomly organizing, or in some form, let's say, not regularly organizing my samples, that doesn't have to mean you have to do it uniformly randomly, is actually can be beneficial, right? Let's look at that. Again, how can we do this? We talked about, right, what are possible sampling patterns. There's a Poisson disk, there's a jittered sampling, stratified sampling, where, right, you subdivide into subpixels, and then you take one there. There's a technique, and again, I only go over them here very quickly because I mentioned them already, and we go into much more detail in the realistic image synthesis. There's a lot you can gain from good sampling patterns here, and particularly the quasi-random numbers. So there's certain sequences, they are deterministic, right? They're not random, they're fully deterministic sequences of numbers, but they have the advantage that they look random. So they're kind of, right, they have certain properties that samples are not too, they don't clump, they don't leave gaps, but there's also no regular pattern. Well, there is some pattern, but it's right, it's not apparent, and it doesn't show up in the sampling and reconstruction. So the Halton sequence, for example, is one such sequence that is fairly simple to use and causes them. And there's another reason why we might want to use such a random or non-regular sampling pattern, because if you look at the distribution of some of the photoreceptors, here in this case, it's from an ape, you see that it has exactly such a structure, right? It has samples, they kind of have roughly an equal distance to each other, but they're not regular, right? There's some randomizations going on. And if you actually look at the Fourier transform, or you just plot the distance from one sample to its neighbors, you see that they roughly have an equal distance to each other. And here's why stochastic sampling is such a great idea. If you have a slowly varying function, right, and you, instead of taking a sample at some point x, you offset a little bit from x. Okay, if the function varies only slowly, then the change in the function value, if you right, at f of x, it's right, if you vary x a little bit, then f of x will not vary a lot, right, because the function varies slowly. So you essentially get almost the same value. If, however, you have a function that varies very quickly, right, so you have, right, very high frequency noise, right, and then you do a random sampling, what are you doing? Well, if you average this over many samples, you're essentially averaging that high frequency function. Right? Let's say you take 100 samples, right? In this case here, you get just the average value out of that, and take 1 over n of the sum of those whatever samples you're taking. So if you have high frequencies, random samples actually converts the high frequencies into an average value of these high frequencies, while for low level, for slowly varying things, it doesn't change much. And here's an example why this works perfectly for images. So I have to explain this a little bit. So in this case here, we're actually sampling a pattern that consists of these triangles. These triangles, and you might not be able to read this, they're 50 pixels high, right? And the width, or the distance between those triangles, is 1.01 pixels. Right? So they're almost exactly 1 pixel apart, just a little bit more. Okay. Now, if you regularly sample that, right, you see what happens here in the center, right? If they align, if the samples just happen to align with the center of the triangle, right? You get all the samples up to the top, right? And if they don't align, you only get a smaller, right? You only get the pixels that are at the lower parts of the triangle. Okay, and so if you now generate an image of that pattern, and you take one sample per pixel, you get this, right? This is strong aliasing now, right? You get this low frequency triangle pattern where there should be a high frequency triangle pattern, but you're not seeing this, right? This is exactly right. The high frequency of the copy shows up as a low frequency signal here. And if you go to the picture below that, right, even doing 16 samples per pixel doesn't really help you here. Yes, you're right. So these are regular samples. And so you see that you get, right, shades of gray here, but they're also regular. And so we haven't talked about the human visual system, but our human visual system, as we'll talk about a little in some later lecture, is extremely good at picking up edges, right? And so the edges between this constant colored regions here, they pop into our eyes, right? So we're attracted to see those artifacts. So that's a really bad idea. On the right-hand side of that signal, here in the top right, we again take a single sample per pixel, only a single sample, right? But it's random. And what do we get? Well, we get something that in the, right, in the lower parts, it's almost all white, right? Because there's a high probability, right? If we randomly sample, there's a high probability because the triangles, the white triangles are wide, right? There's a high probability of hitting the white area. And in the top part, there's a, right, the triangle, the white triangle is small. And so there's high probability of hitting the black background. So essentially what we see, and here's another factor that comes in from the human visual system, we essentially integrate over these areas, right? And so essentially what you are seeing, right, if you squeeze your eyes a little bit, right, then this is like a linear ramp from, right, all white at the bottom to all white at the top. And this only gets better if you take more samples, because now this ramp is even smoother, right? You have less random samples here. Essentially what this tells you is randomly sampling, or I should be more careful, irregularly sampling a pixel is good for us for several reasons, right? First of all, we remove these correlation, these aliasing artifacts, right? And even better, because we kind of integrate over the signal of the high frequency signal, if there is high frequencies. And even better, we benefit from the human visual system that we are not really tracking the individual white dots, but we're kind of integrating over that, and we're seeing the average value, if you want. And the same is actually true also in the temporal domain, right? Here again, so we have a white rectangle moving from left to right, okay? And we're taking samples in time. In the top left image, we take a single sample in time, and we don't do any jittering. So we happen to take the middle time interval, or a sample in the middle of the time interval. So we get one copy of that white rectangle or square, actually, that's sitting in the center, right? So for every pixel we sample at exactly the same time, which is that middle 0.5 time, right, if the rectangle moves across the image from 0 to 1. If we, instead of take a single sample per pixel, so it's 16 samples in this case, right? What we get is 16 copies of this one, of this square, okay? Because, right, we take 16 regular samples in the time domain, and yes, either one of those or more of those samples overlap with the rectangle, or they don't. And so we get these regular copies of the rectangle, right? As if you've drawn the rectangle 16 times and then kind of merged the results. If, however, right? And that's on the right-hand side now. If, again, now we take a point, if we take the sample random in the time domain at each pixel, right? Again, right, sometimes, depending on where the pixel is at, where the square is at that time, right? There is a higher or not so high probability of hitting this. And so we're kind of averaging over this. And what you get is this smooth, constant gray, more or less constant gray band here. And it tapers off to the left and to the right because, well, I mean, there was no triangle out there. So we also get that effect. And if we take more samples, it just gets smoother, right? And it appears smoother to our eye, which is great. Yes, and just to round things up, so here we have we have a sharp edge, infinite frequencies, right? We've rotated that edge a little bit, or is it rectangle or whatever? Rotated a little bit, so we get these nice staircases, right? Of course, we use to kind of illustrate this, we use a very low sampling frequency here, or very coarse pixel grid. So if we only take a single sample and then color the entire pixel with that color, so essentially we use a box filter for reconstruction, we get these staircases, right? And they're very apparent. If, however, we use a regular 3x3 pattern, so we're spending almost an order of magnitude more work, right? What we are getting here now is, right? We don't get this edge exactly aligning with our subpixel, right? But we're not getting the full benefit either. And so you see here that you don't actually get all of the levels of gray, all of the 10 levels of gray that you could get for this edge, but essentially there's just wider steps here with slightly different gray values. So that's obviously much better, right? But since our eyes are so sensitive to regular patterns, again, it kind of jumps out. These, even though they kind of look like blurred edges, they still jump out to us. And only if you go to 7x7 sampling, then it looks like an almost smooth edge now, right? But we're doing, right, 50 times the work now. It's probably not a good idea. If, however, instead of a regular sampling pattern in a pixel, right, we do, for instance, jittered sampling, like a 3x3 grid, right? In this case, yes, you'll see there is some noise in the edge, so it's not kind of nice and smooth because, right, we randomly sample different at different locations in every pixel, but it almost, right, if you squeeze the eye a little bit, it looks almost as good as the 7x7 regular sampling above that, even though we do 5 times less work, roughly. And if you go to 7x7 jittered sampling, we get an almost perfectly smooth edge with no aliasing in this case. And remember, this is a hard edge, so we have infinite frequencies, right? But a 7x7 sampling pattern already took care of that. And the jitter sampling, if you compare the 7x7 regular, we still very clearly see the staircase pattern, right? This is almost completely gone in the jittered 7x7. So jittering, or let's say irregular sampling, has a clear advantage here. We don't have a good theory for that, right? For regular sampling, we have Fourier transforms, and we can argue about sampling pattern, Nyquist limit, blah, 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 right? We've done that today in the last lecture. For the jitter sampling, we don't really, or irregular sampling, we don't really have a very good theory of the same kind. There's various results that help us, and it also includes the human visual system, which is complex in the first place. So things are not as clear cut here, but just the evidence of that I demonstrated here is indicating that it's a good idea to do that. With that, we only have a couple of minutes left. Any other questions? I think I'm done for today. Any questions? So if you're more interested in sampling, we will have separate several lectures looking specifically at sampling in the realistic image synthesis lecture course in next semester. So also Gurpreet Singh, who is a researcher at the Max Planck Institute next door, he is an expert on sampling, and he will actually do some of those lectures. So there's
Philip, there is yet another question.
yeah, since midterm exam is canceled, what are we going to do on next Thursday? Nothing. We're just canceling that that lecture because I couldn't be here anyway, so we're just canceling that lecture. So we keep the normal program. The reason behind canceling that is kind of obvious. There's because of the pandemic, a lot of people wouldn't have a hard time making it here, so we're canceling the midterm because we can only do this in a reasonable way here in presence, and obviously there's only few of you really here, and others couldn't even come here, so the effort for doing this just doesn't pay off. So what I can recommend instead is that you just go through the tutorials in more detail. And when in some sense the midterm exam is just feedback to you about how good apparently did you understand things so far. And so going through the tutorials gives you at least some of that value. So it's essentially less service to you, right? You maybe don't see it as a service, but as an additional burden on what you have to do. But it's really meant to give you feedback whether you're really understanding things, because right at the end it's the exam that then counts. So just do yourself a favor and make sure that you understand things here, and don't fool yourself that you think you understand it and then at the exam find out maybe you don't. Feel free to use the tutorials also to do things and ask questions. Go through the tutorials, make sure you've done all of those. Good, yeah, that's all we can do here. Any other questions?
I have a question
Yes.
about jittering. So if we are jittering the positions randomly, what's the difference between jittering sampling or random sampling? I didn't understand that.
And you couldn't. I wasn't explaining that part. In this lecture we don't. So sorry, I have to repeat the question. The question was what's the differences between dithered sampling and some of the other sampling patterns. I didn't really talk too much about that, and this is beyond the scope of what we can do in this lecture here. If you are more interested, but let me summarize this maybe in a different way. So what you want is you want sampling patterns where the samples are well distributed across the pixel, but where there's no regular patterns in that sampling pattern, right? So no n by n grid, for example, right, in the worst case. So you want them equally or smoothly distributed across the pixel, but without any obvious higher level pattern in there, which could be picked up and then result in less of a good result in the pixel in terms of correlation, for instance, with an edge or something. It essentially boils down to correlation, avoiding correlation between the samples you're taking and any geometry, any features in the geometry or in the function that you're reconstructing here in this case. If you want to know more, take the RISC course and wait for the lectures on sampling by Gurpreet, and he will tell you much more than you maybe wanted to see. No, he's doing a great job and really going into all the details about that. We just don't have the time here in this lecture. This is why it's an advanced lecture. Okay, thank you very much for staying around a little bit longer. And I guess we'll see you on Monday then. And we'll do it in person. We'll continue doing it in person. Thank you. Have a good day. Thanks.